Okay, the first technique of integration, and by far the most important one, is the substitution method. Okay, and we have let's say a function f of x, and we have its derivative, and we have to integrate this with respect to x. Alright, so what I can do here is that if I put f of x equals to p, okay, and then I differentiate both sides. Now p is some variable which I have chosen to be equal to f of x, and now I differentiate this equation with respect to p. Okay, with respect to p. So what I get here is that I get f dash x dx over dp, right, since I'm differentiating with respect to p. So the derivative of p with respect to p is 1, and so f dash x d of x is simply dp, right, which, and this is something that I have in my integral. I have f dash x d of x here, so I can replace f of x by p, since that's what I've taken, and I can replace f dash x d of x by dp. So what I get here is I get p dp, which I already know the integral to p, and that's okay, that's p, simply p squared over 2. So what we're doing here is that we're converting the integral into a form that we are already familiar with, and then we can just replace p by f of x from, say, equation 1. Okay, so you get f of x squared over 2 plus c. That's your answer. You can just put in f of x whatever it's given to you. So let me see if it matters where the f of x or the function is present. Let's say it's present in the denominator. Okay, what do we do then? We just put f of x equal to p, the same thing, and you get, okay, you just follow these steps and you get f dash x d of x equals to dp, and f dash x d of x is still present there in the numerator, so I can just put this equal to dp, and I can put this equal to p. So what I get here is that I get dp over p, which I already know it's the natural log of p, and then I replace p by f of x. So it does not matter where the function is present. Okay, it may also be present inside another function. Let's say we have x 2x times sine of x squared dx. Okay, and I have to integrate this. So this function is present inside the sine function, and its derivative is present in the product with d of x. Okay, I'll just rewrite it. It's 2x dx. So what is this? This is f dash x dx, where fx is x squared. Okay, so if I put x squared equals to p, then this whole thing becomes dp. Okay, the same procedure that we did here. Okay, these 3 steps, right? So what do we get here? We get I'll just go there. Okay, sorry for messing it up. Anyways, I get a sine p dp, and I already know the integral. It's cos, okay, with a negative, sorry, right? So the function can be present inside another function. Let me take an example for this. Let me take sine hyperbolic log of x, okay, it's the natural log, over x, and I have to integrate this with respect to x. Okay, so the function here, I'll take log of x as b. Now how do I choose what to take, what to substitute? I choose that by seeing that the derivative of that function which I'm going to choose should be present in the product with d of x, and it's right there, over there. Okay, the derivative of log x is 1 over x, and it's present in the product with d of x. So p equals log of x, and now you differentiate both sides with respect to p. The derivative of p with respect to p is simply 1. The derivative of log of x is 1 over x dx over dp. Since you're differentiating with respect to another variable, you're not differentiating with respect to x, differentiating with respect to another variable, that is p. Okay, so dp goes there and you're left with 1 over x d of x, which is present right there in the integral. So I can replace this whole thing by dp, and I can replace log of x by p, since I've taken p to be log of x. Okay, so what do I get here? I get a sine hyperbolic p times dp, or you're actually this is a notation, but to make it clear I'll use as a product, because f dash x and dx should be present in the product. Okay, or you can also say that the derivative should be present with d of x, just as we saw there. Okay, this should be present with d of x. Anyways, okay, and now the integral of sine hyperbolic is simply cos hyperbolic, which, if you're not familiar with that, you can watch the video on hyperbolic functions, plus c, and that's the answer. Okay, I'll take another example. Let me take the integral of x sine pi x squared plus 16 e to the power 7 plus 1. Okay, something like that. Now it looks complicated, but simply if I put this whole thing equal to p, okay, pi x squared plus 16 e to the 7 plus 1 equals to p, and then you differentiate both sides with respect to p, this whole thing is a constant, so its derivative just vanishes. You're left with 2 pi x, and since you're differentiating with respect to another variable p, you get a dx over dp here equals to 1, since the derivative of p with respect to p is 1. So 2 pi x dx equals to dp, and hence, since I have x dx here, I'll find out what x dx is. It's dp over 2 pi. Okay, so now what I'm going to do is that I'm going to replace this whole thing by p, since that's what I've taken it to be, and I'm going to replace x dx with this. Okay, that is x dx. So what I get here, okay, I get the integral of, since x dx are together, I'm going to write it as dp over 2 pi. Okay, that's x dx, and sine of this whole thing, which is right there, which is p. Okay, and 1 over 2 pi is just a constant, so it comes out of the integral sine of p dp, and I hope you know the integral of sine of p. It's negative cos p plus c. Okay, and that's the answer. In fact, you can always replace p by pi x squared plus 16 e to the 7 plus 1 in the answer, because p is something that you've chosen yourself. It was not there in the question. Okay, let's say this is the problem you're given, and p is not there in the problem. It's something that you've chosen yourself. So at the last step, you should always replace p by whatever was given in the question, whatever variable was given in the question. Okay,